Hello, welcome everyone to this third and last day of the heterogeneous programming with SYCL workshop. Sorry for this little trouble at the beginning. We had some issues setting up the breakout rooms. That's now fixed. We hope so. Let's move forward with today. Today's a little bit shorter day, so we ended up past 11 instead of 12:30. But of course, if there are many questions coming in, we can keep going longer. Depends a bit on if there are questions or not. So let's recap a bit what we saw yesterday. We went into how to express parallelism with SYCL. So we had a look at how we would use the parallel for method on the queue or on most often on the handler class to submit work to the queue. And we saw that there's three forms of parallel for, but we only went into the details of two of them. So the basic form and the ND range, and dimensional range form. So the basic form accepts a range of execution, which is 1, 2, or 3-dimensional. And the range of execution basically maps to the data that we are handling and describes to the runtime how basically the pass through the data and the actions through the data that the kernel needs to take are structured. We saw that the basic version of the parallel for can help us or is the idiomatic way of expressing loops where we don't need fine-grained control over memory access. So this is, of course, not something that is ideal in many cases because it might lead to unoptimal memory access or wasteful memory accesses, as we saw in the first example with the matrix multiplication, where we were rereading the same data over and over again while traversing our matrices to compute the multiplication. So the next step is to move towards a more complex form of parallel for, where we use an n-dimensional range, where we can specify the ND range in giving two subranges, so the global and the local range. So what the local range does for us is group the work items together into work groups, such that each work group can have access to finer grained control over memory access. We saw that this can be achieved through synchronization primitives, which are collective functions, which we will see together again shortly. And through the use of local memory and local ranges, we can have a chance at optimizing further our kernels if we know that there are more efficient memory access patterns. And that's what we saw in the additional matrix multiplication exercises, where by using a local range, we can kind of load together sections of the operand matrices so that we don't reread the same data over and over again. And furthermore, we can also use local accessor types, which address into local workgroup local memory, which is a faster resource where we can load data for the whole workgroup to work on instead of trying to address global memory, which is a slower resource. So yesterday we ended the day by looking at a port of kind of a real-world app. So this heat equation mini app. I'm not sure if many of you managed to provide a port. Of course, there was a solution, a proposed solution to this exercise that you could have looked into. What I want to do now before we move forward is to have a look at this proposed solution and kind of show what I did to come up with this port. The last thing that we saw yesterday before leaving was that I will now log on to Carolina. That we saw yesterday is that the execution time of the port was actually 3 to 4 times slower than the serial version. So something is seriously wrong with this port, and it is Not surprising, because I designed it to be suboptimal so that we can have something to work on when we try to look at the performance profiling later today. So let's see. So this is my work folder. What am I gonna do? So I will stash my changes, and then I will fetch the origin. I will pull minus minus rebase because I pushed some updates yesterday. Then I will pop the stash. Okay, great. So if you go into code content day 2 and it was 06 equal heat equation. So let's see what are the main changes from the serial version. So I start by including the SYCL header and using namespace SYCL. Of course, using namespace SYCL, as I said at the very beginning, is not usually a very good idea to do it in global scope, but this is the main.cpp file, so it's fine. This is not going to be included in other files, so it's something that is not that dangerous. So the code uses a field data structure to hold basically the data for a given discretization of the square plate. For the temperature field, and here I declare 2 for the current and previous time steps, and then I initialize them with the boundary conditions that are set. Some of these are set by default. Calculate the average temperature, define the parameters, so the diffusivity constant and the time step. So the time step is calculated based on the space discretization. Then what do? I create a queue. So in the proposed solution, I didn't map it to the GPU because I was relying on hipSYCL to do it for us. But it's probably a better idea to be explicit at this level and just say Q on the GPU selector. So we make sure that we end up on the GPU. And then I take the start time and I start the time evolution iteration. So we said yesterday that the time evolution is essentially serial because I cannot parallelize this loop. Since I need the solution at the previous step to calculate the one at the current step. So what we work on to parallelize or to port to GPU is in the core evolution kernel, so on this evolve function. So you see here that from the serial version, what changes that now I'm passing a Q parameter into the evolve function. Everything else stayed the same. So I still pass the field data structure, current and previous, the diffusivity constant and the time step in. And then once I'm done, I check whether I should write the field to a file. This is for the PNG visualization. We don't need to worry about this. And then before moving on to the next step, I swap the current and previous iteration of the field. So I basically take the data and swap it between the two data structures. Once I'm done with the time evolution, I take the stop timer, and this is what gives us basically the average time per iteration. Or the total time. Here I'm bringing the total time spent during the iterations. Okay. So this is in the main function. So the modifications that to put was basically to set up for using SYCL, so include and using namespace, and then create a queue. Now the next step is to basically modify this evolve kernel. So this is in the core.cpp file. And of course, we also need to modify the definition of the function signature in the header file, but that the compiler will complain about that, so we will know when we compile. So this evolve kernel or function, sorry, that was inaccurate to me. So we add these initial arguments q and q. So we pass by reference the q. And from the current and previous data structures, we calculate basically the sizes of the grid and the denominator for the 5-point stencil that we're gonna to use. So delta x squared and delta y squared. And then within that, we open a new scope as we've done many times before, and declare buffers for the current and previous data. and this will point to the data that is being held by these field data structures. So two things to note. So one thing to note here is that the data structure itself, it's two-dimensional, so we map it to a range 2. And even though we have a discretization with nx points in the x direction and ny points in the y direction, the range is nx plus 2 times ny plus 2. And that is because, as I was remarking yesterday, we have to make sure that when we apply the stencil on the border of the grid, we don't fall off the grid. So we put some buffer region around of one cell to the left, one cell to the right, one cell to the bottom, and one cell extra to the top, and this justifies the +2. So this is basically to make sure that the stencil application is always valid without having to impose periodic boundary conditions, which would be a bit more involved. Once we have the buffers ready, we can submit to the queue. Again, the same thing, queue.submit, and then we open this lambda that will give us a handler object. And within the handler, we declare accessors to the buffers. So the current buffer is read-write, while the previous buffer is read-only. So probably we could have made the current buffer write-only, but that's something that would probably not be understood by the compiler, so would be converted to read-write. So we leave it like that. And then we submit the parallel 4. So this is a very basic port, so I'm not trying to do anything fancy with n-dimensional ranges. I just go for the basic data parallel 4 construct, so it passes a 2-dimensional range. And now the data structures are a bit larger, meaning that their range is nx plus 2 times ny plus 2, but the points to which I actually need to apply the stencil and update during the loop are just the ones within the grid that I've defined. So the range here of the parallel 4 is nx times ny, and not nx plus 2 times ny plus 2. Then we define our kernel. So this is again a lambda that captures by value and accept an ID2 object, which I call ID. And then I get out my indices, j and I. Again, I need to offset for the fact that I actually have one element more at the beginning of our list that I should not apply the stencil to. So that's why there's a +1 here. And then I finally apply the stencil. So I get from the accessor to the current field, I update the ji element based on the value of the previous ji plus the time step times the diffusivity times the value of the Laplacian approximated with the stencil. And this is it for the definition of the kernel. So this is not that much different from the serial version. I actually think that, I just copy-pasted the code and changed the name of the data structure used here to acc underscore prev instead of just using prev. And once we're done with this submission, I just close the scope, and that's it. So this is our initial port. So why is this so slow? We will see later with the profile that it's the profile will show us exactly where things are going wrong. But the thing is that this opening and closing of a scope every time we call the evolve function means that these buffers will first perform a copy from the host to the device when creating the buffer. And when the buffers are destroyed, they will trigger another copy from device to the host. So this means that every time that we call the time step in loop, we're making 2 copies per data structure even. So we are copying twice the current, the data in the current data structure and twice data in the previous data structure. Only this is, of course, unnecessary because we know that all we need is just to have 2 buffers that are of nx plus 2 and ny plus 2 size. They can be resident on the GPU, and we just need to copy them back and forth once before the time stepping iterations and once after the time stepping iterations when we want to retrieve the results to the host. Of course, the situation is slightly more complicated by the fact that we want to allow in the main function to write these fields to file. So we might have to do copies at different intervals, not just at the end, at the beginning and at the end, but that's a detail. So one obvious thing that we should do when we try to optimize this kernel is to avoid so many copies. So to make the code slightly smarter so that we copy once before we enter in the time stepping loop and once we are done with the time evolution. So this is what we will do, not in this section, but in the next section after we looked at the profile for this application to make sure that our hunch that the reason why this is suboptimal is actually because of the memory copies. So after this long-winded introduction, I think we can go to the actual next section. The next, I click on next and I put in presentation mode. And so yesterday, before we looked at the heat equation mini app, what we saw in when talking about the task graph and synchronization was a way to use workgroup local memory, and the essential take-home message from that part that we discussed yesterday was that if you want to use workgroup local memory, one, you need to make sure that the device that you're actually targeting does have such kind of scratch memory available. Because if not, the SYCL runtime will basically map it to global memory. So instead of using fast local memory, you will be still addressing into global memory, and that doesn't give you any advantage. It will just make your code more complicated. And second, which is probably even more important, that this memory is not guaranteed to be consistent between accesses. And this is something that the standard does not mandate because it would come at a huge cost at runtime. So what you need to do is whenever you read from local workgroup local memory or write to, you need to put a barrier at the item level so that every item that uses local memory has to wait at the barrier before moving forward, so that you make sure that the view across the workgroup of the memory is consistent between all the different items. So there are other ways to achieve this in SYCL, this kind of kernel level communication between work items, and this is through the use of subgroups. So this is the same figure that we saw yesterday when describing what an n-dimensional range is. So we have a bunch of work items, in this case 8 times 8 times 8, 512 work items, and within this global range of work items we define a local range which gives us a 4 by 4 by 4 work group of work items. So within this work group, there is a further level of subdivision, which is called a subgroup. A subgroup is always one-dimensional. It's always aligned on to the contiguous dimension of the work group to which it belongs. And it's basically a way it can be used for further optimizations. So the number of work items that we have, it's basically the total size of the ND range. So it's given by the global range. And in our example, it's 512. And if the SYCL implementation that you have, that you're working with does support the further subdivision into subgroups, you can use them to have another way of working with local memory, essentially. So these are, as I'll repeat myself, these are always one-dimensional and laid along the contiguous dimension of the parent workgroup. So the size is implementation dependent. So at variance with what you can do with an ND range, where you have power over defining how big the global range is and how big the local range should be, the dimension of the subgroups is defined by the implementation. So you cannot set it beforehand. You can probe it from the get info method, as this snippet shows. so that you make sure that when you're using it, you use it in the optimal way, so that you use the full size or divisor of its size. So you cannot set it in the ND range constructor, but you can get it as an info item. So why should we bother with this next level of kind of abstraction in the subdivision of the work items if we cannot set the size of this subgroup anyway? So the subgroups are, again, groupings of work items within the work group, but they come with additional scheduling guarantees. So this is what makes them different and useful and interesting. So the most obvious of these guarantees is that all the work items in the subgroup execute together on the same hardware. So this is a guarantee that you don't have for the whole work group. So we know that the work items are in the work group are not guaranteed to make progress together. Because the runtime might decide to schedule them in a way that makes the most sense for the heuristics that the runtime uses. So this means, since they execute together, that there is limited or no need to explicitly synchronize these work items using barriers, even though it might be needed at some point. In some cases, sorry. So if we think about the tiled matrix multiplication exercise, again, where we had to put a barrier right after loading the data into the tile and right after reading from the tile, so that meant 2 barrier per parallel 4 iteration, so to speak. In this case, we can see that it wouldn't be needed. You would kind of communicate this data in a different way, and I'll show it soon. Since all the details about how the subgroups are implemented are left to the people that write the SYCL compilers, you might find out that they actually enjoy even further execution guarantees, and that the implementer might have written functions that are to work with subgroups that are perform further performance optimizations to what you could potentially come up if you just limited yourself to using workgroup local memory. So one of these things, like this performance optimization that the vendor might apply, is that communication and synchronization between subgroups within a subgroup might be more efficient than writing to local memory and reading from local memory by hand using barriers. So this is, of course, something that you need to measure. You would need to run through the profiler to see where you get the best performance. It's not always the case that with a subgroup you get better performance by using workgroup local memory. So how do we get a handle on this subgroup? So within a parallel 4, you have an ND item, and the ND item will belong to a given workgroup in the global ND range and also to a subgroup. So whenever you get an ND item object, you can call the get subgroup method to get a handle to an object of subgroup type. So you would do something like this. You have a parallel 4 with an ND range and kernel accepting an item. And then within that thing, you would do auto sg equals it.get subgroup. And there you have your subgroup. So again, you cannot modify the size of the subgroup. This is decided by implementation, but you can use it like this. So when we use workgroup local memory, we have to explicitly set its value and synchronize the memory view across the work group using a barrier. So this is what we were doing yesterday. So we have a tile, and that is in a local accessor, so workgroup local memory. We read some stuff from global memory through an accessor to matrix A, and then we call it. It is the handle for the item dot barrier, and then all the items have to wait at that point. So the faster ones will wait a bit longer for the slower to get through the loading of the data to the tile. And then we would use it, okay? So we used it yesterday in the inner loop to compute the product with the matrix B, and then after doing this, we would have to put another barrier to make sure that execution is complete for all the items in the workgroup before moving forward. So when using subgroups, we use subgroup collective functions instead. So the barrier is already kind of a collective because all the items must go through the barrier, must wait there. But for subgroups, we have access to more kinds of collectives. Some of the names might be familiar if you're familiar with MPI, because the concepts are kind of similar. So a work item in the subgroups would load data and then broadcast it to communicate it to all the elements in its subgroup. So what we would get would be a subgroup that contains all same elements. So we load the tile again as before. So auto tile A. Now this is not an accessor anymore. This is a simple. This is the same type that is returned by calling the accessor with these indices, and then within the tile size loop, we would compute the sum not by just indexing tile A, but by broadcasting its value for the given index. So the group broadcast function, it's applicable not only to subgroups, but also to groups, because a subgroup is a subtype of the group type, of course. So it takes 3 arguments: the group itself, the element that we want to broadcast, and the local ID. So the local ID, in our case K, in this little example, would be the index in tile A, and this would be communicated to all the elements in the subgroup. So looking at this, since all the elements in the subgroup, all the items that are in this subgroup will go through the same loop, they all will perform the broadcast. That's why it's called a collective. And that also means that the local ID must be the same for all work items for this to work. Otherwise, there would be, of course, ambiguities in the broadcast who's getting what element where. So what I would like you to do now is to work on this exercise. This is again the matrix multiplication exercise. So what I would like you to try is to look at the tile, the matrix multiplication that we saw yesterday, and instead modify it from using workgroup local memory to using subgroups and group broadcasts. So again, as usual, as before, we have a day 3 folder in the repository, and then there's a 00 subgroup matmul folder with a scaffold C++ file. There's some fix me prompts for you to complete. So here there's some instructions. The thing that I would like you to note is at the bottom where basically what to do with the item, with the ND item that we get to get the subgroup, and the indexing, and basically how to use the group broadcast that I was showing before. So this is a bit more complete set of instructions. And as usual, if you want, you can just peek into the solution subfolder to see how these things work. So I haven't run any speed comparison between the workgroup local memory and the subgroup, but that's something that you are welcome to do in the breakout rooms if you just want to work with solution directly. So I would say that we open the breakout rooms for 15 minutes now. I think we're a bit over time because I did a lot of talking on the heat equation. But we can do 15-minute breakout rooms and then go on a 10-minute break right after. Okay, so I hope you had time to hydrate during this break. I see there's a couple of questions in the ACMD, and someone is already answering. So for the second question, yes, I've tried as well to use OpenMP. OpenMP does not define subgroups in the standard itself, does not have an explicit way to use local memory as the GPU do, probably because it doesn't map well to the hardware in a generic way. So it will compile with hipSYCL. There will be a warning, however, and then when you try to run, it just crashes because it cannot understand how to do that. So the code is not perfect. The example, what one should do before using any of these abstraction is to probe the queue and the device to see whether subgroups are available and what size they are. Okay, so the code should have some if statements to make sure that you actually get to the correct code path if you want to use subgroups, and if the subgroups are not available, you just need to crash early instead of crashing in the middle of execution. So that's question 2. Question 1. So why the local range is 1D? It's 1D because we're gonna read one tile from one row at a time. We're not going to read multiple rows. And that's why I made it 2D. And subgroups cannot be two-dimensional, so they're strictly one-dimensional, and they're aligned, as I said, on the contiguous dimension, the work group. So that's like a limitation. Or I mean, they're made to be this way. So we have to live with that. Maybe in some next iteration of the standard, things will change. But probably not. Okay. So I will not go through the solution of that exercise because I think this is more interesting to look at. Profiling SYCL applications, because this also leads us to kind of getting proof of why our heat equation mini-app was so damn slow. So as proof of what is usually the case, that like the first version of a port of a code to execute on a new architecture or parallel port is not usually extremely satisfactory when it comes to performance. In our case, it's absolutely abysmal. So it's not great, that heat equation mini-app port. And it's not surprising because, of course, there's always a question of, is the algorithm the appropriate one? Is the most efficient one to use for the given problem and for the given hardware? So that's one thing that one can try to kind of discuss and maybe figure out with pen and paper. But always when we write code, we need to measure the performance and not just the timing. I mean, the time to solution is important, but we also need to make sure that we are actually using the hardware as efficiently as possible, meaning that we might get a speed up if we run on the GPU, but are we actually using the GPU in the correct way? Are we keeping all the compute units as busy as possible most of the time? So algorithm design, yes, that's important. That's something that we can do on a whiteboard or pen and paper, but measuring and actually writing code and running code and measuring the performance through specialized tools, it's as almost as important part of the job of writing performant code for HPC. So what one does usually, and you might already be experts in this, so what I'm saying will not be news for many of you, is to use so-called performance profiling. So because that helps us get answers to many of these questions, not just is this code globally faster than another version that I have, or is this code going to perform better if I have a larger problem at hand, but also how am I using the memory? Are the memory accesses done in an optimal fashion? Where can I improve? How can I identify bottlenecks? And is there any way that the software can analyze these bottlenecks and suggest ways to fix it? So how do we do this with SYCL? Okay. So one way of doing that is to use so-called SYCL events. So we've seen events when we talked about task graph as a way of basically influencing the way the task graph is arranged by the runtime, because the execution in SYCL is asynchronous. So when we submit work to the queue, we don't get the results immediately, but instead the submit method will return an event, and then we can wait on the event to make sure that that it goes to completion. But on top of this, we can also use events to, for example, get timings or to get information of when a kernel is being submitted, when it starts execution, and so on. So to do so, we need to initialize a queue object. We can put in a selector, of course, and then the optional argument that we kind of glanced over at the very beginning, so-called property list of the queue can be used to set a list of properties that the queue should have. And the one that one wants to use for profiling is the enable profiling property. So this basically tells the queue that it needs to kind of keep trace of what is being submitted to the queue for this timing information. So basically, the enable profiling property will basically tell whenever you get an event, please also collect the timestamp or when that event happened. And this collection of timestamps happens for work submission. So when we call queue.submit to put some work on the queue, when the execution of that work starts and when the execution stops. So we have these three timestamps that we can use to kind of reconstruct what the flow of events was and at what time those happen. And of course, if you take difference of timestamps, we can get how long time was spent in any of these steps. So how does this work? Okay, we create the queue with the property of profiling. Then when we submit, instead of just calling queue.submit, we save the event in a variable, in this case e, auto e equals queue.submit. If we want to get timing, we need again to recall that execution is asynchronous. So before collecting the profiling info, we need to wait on the event. And after the wait, we can call the get profiling info method on the event to get the timestamp. So the timestamps are in nanoseconds, and the get profiling info accepts a template parameter to understand which of the timestamps to return. So command submit is the timestamp in nanoseconds when the associated command group was submitted to the queue. So in this example here, this timestamp here will tell us at what time the submit command was issued. And then we have command start and command end. As they say, they collect the timestamps in nanosecond when the action that was associated with the command group, for example, a parallel for, started execution, and when it ended execution, respectively. So what I would like to do now is to modify or look at the SYCL equation port, hit equation SYCL port, and add this event-based profiling to it. So you can copy the port in the day2 folder to a new event profiling folder. And then we modify the mini app to enable the queue for profiling, and we collect the events related to every time we call basically the evolve kernel. Yes. So this basically will collect all the timestamps for every time we submit work to the queue and every time we execute the what was I going to say? Where we execute the kernel, the stencil kernel. Yes, that's what the word I was looking for. Okay, so this one we can do in breakout rooms. I don't think I have a proposed solution for this. Sorry for that. I thought that it was in the repository, but I didn't check it in. So let's start breakout rooms for 15 minutes, and then let's see how far we get in breakout rooms, and I can give a summary at the end of the timings. The questions here have been answered, so I'll just go here. So contrary to what I said and what's written on the web page, there actually is folder with the full SYCL events profiling enabled and working. So if you go to this day 301 SYCL events profiling, you will see the full solution to the exercise, so to speak. And if we look at that, what I'm doing there is to initialize the queue with the profiling interface enabled. So here the runtime knows that it needs to collect the timestamps that I was talking about before. And in this case, since I'm not looking to get super detailed info, I'm just accumulating the total time spent in common group submission and in kernel execution. So I declare these two float variables outside the time stepping loop. Inside the loop, this is where things change a little bit. So the evolve function now returns an event, auto e equals evolve, blah, blah, blah. So inside the evolve function, one needs to capture the events that comes from q.submit to be able to do this. Then I put a wait statement. So the wait, it can probably be removed because of the way we structure the evolve kernel. We have everything happening in a new scope through buffers, and when the buffer goes out of scope, it triggers a device to host copy. So that means that it will wait on whatever was happening in the kernel submitted to the queue before returning. So probably the wait here is unnecessary, but it's good practice to put it there just to signal to whoever reads the code after you that you know we need this stuff to be completed before moving forward. And that is because we want to get exact or as accurate as possible timing information out of the event. So to do that, you call the get profiling function to get the submission time point, the kernel execution start time point, and the ending time point. And then what we do after getting that information, we use it to compute how much time was spent between submitting, or how much time passed between submitting to the queue and actually starting execution of the kernel, and we convert it to milliseconds, and how much time was spent in executing the actual kernel, so from start to finish. And then the further modifications that I made are just to print this information. So if you compile and run for the CUDA platform, so to run on one of the GPUs on Carolina, you will see a printout like this. So it's running. So this tells me that, okay, so the total execution time, we're still 2 to 4 times slower than the serial version. So this port is really bad. It's, I mean, okay, we knew that already, that it was bad. So, and we kind of understood from the way the evolve kernel was written that the performance loss was coming from the fact that we were triggering 2 copies in the device and 2 copies out of the device for each of the steps in the time evolution. So that was our hunch by just looking at the code without measuring anything. This kind of confirms it because the time spent in submission, total time spent in submission, and total time spent in kernel execution is actually a fraction of the total execution time. So this kind of points us in the direction of confirming that there's something wrong going on about our memory allocations and how we manage the memory. However, this is as far as we can go with the events profiling API of SYCL, because we cannot profile how much time is spent into the actual memory allocations, unless, of course, we create events for timing that explicitly. This is something that we most likely do not want to do, because so to get to this analysis of our code, we needed to modify it quite heavily. Okay, so we needed to modify the function that performs the execution such that the event was actually returned and not discarded. So this is something that, of course, you can take into account when you design your code, that the event is always passed through, so that you don't need to go deep in and do these modifications when you need. That's, yeah, something that programmers might take into account, but it's definitely not practical to go into a code that already exists and make these kind of large modifications to get timing information. Even though it's valuable information, There are other tools that can help you do this job, and my suggestion is that you get acquainted with using these tools, because they provide even more information than what you can get from this simple profiling API. So it's usual then to rely on something that is called sampling profilers that collect events at a lower level, so usually at the kernel level. So whenever instructions are sent for execution to the kernel, there's a program that kind of captures every so often what is happening, and then can manage to aggregate this information to provide you with a global overview of what's happening in your code at many of these levels, not just how much time I spent in executing my kernel, but also how much time I spent in allocating and which thread instigated the allocation and so on, and data movement. So sampling profiler accumulates statistical measures on certain given so-called counters. So a counter might be, for example, number of reads from a specific section of memory and so on. So memory loads and stores, register occupancy, and they provide a final report to the user. And this final report is an aggregation of these counters with some statistical uncertainty, because these work by sampling the execution of the program. So they do introduce some execution overhead, of course, because they're doing more stuff than just what your code is supposed to do. But whatever information they provide can be very detailed and very useful in guiding the way you optimize. So these tools sometimes are not very easy to learn to use, but they're definitely worth your effort. So, and there is not one that I would suggest to learn, because they usually provide kind of complementary information. Some of them are tailored for specific platforms, so it can be used either only on those or have serious limitations on other platforms. So here I give kind of an incomplete list. Some of these tools are proprietary. So for example, Intel vTune, which is especially suited for Intel CPUs, is proprietary code, but I think you can download it for free these days. Then there's AMD uProf, which is similar to vTune, but targeted to AMD CPUs. NVIDIA Inside Systems, it's what we will use today, provides command line tools and also a graphical user interface for performance profiling of GPU code written in CUDA. And I think in newer versions, it can also do some CPU profiling, but I've never used that myself, so I will not comment. And if you're using AMD GPUs, there's AMD RockProf, which is just a command line tool that produces some JSON files and CSV with the statistical information on the counters that it collects. And then last on this list, but neither list nor the list is much longer, so there's many more tools, but I just want to give an overview. So-called Liquid. So this is free and open source, and it's a set of command line tools that works on many different CPU architectures and NVIDIA GPUs, and it's also able to collect performance information for MPI-based code. So if you're interested in profiling that, you should look into this Liquid. So in the very first section of this workshop, we tried to answer the question with this SYCL, and we saw that SYCL is a standard. It's a header-only extension to C++ for parallelism, but it's also a compiler. So in these compilers produce code that relies on low-level backends that produce parallel code for the native hardware and the native software stack for the hardware. So when using hipSYCL, as we've done so far, we know that we can generate code for CUDA, OpenMP, or the ROCm stack, which means that at the end of the day, what is being executed is actually CUDA code that was generated by somebody else. In this case, the compiler. So what does that mean? It means that whatever tool is available to profile native code for this hardware, so in our case, CUDA, that would mean the NVIDIA Inside Systems, we can use the native profiler that you would use if we had written CUDA code by ourselves. So we can run equally well our SYCL code through the NVIDIA profiler to get profiling information. And that would give us much more detail on what is happening and how to understand where the performance loss is coming. So what I would like to do now is to go back to this day 2 06 SYCL equation folder to basically the solution, proposed solution that we were looking at this morning, and do not modify anything, just compile it and try to run it through the profiler. And then we can load the profiling information in the GUI, and we can analyze the GUI. We can analyze the profile through the GUI to see what's happening. And here I have a screenshot of what is happening, but you will see the same once we try to run it ourselves, that basically the overwhelming majority of the time is spent in memory copies. So, and this is basically what we should try to fix. Yes, so let's try to run the profiler on this example, and I think we can take maybe 20 minutes in the breakout rooms to do this. Not because it takes long to run the profiler, but because trying to get the graphical session might take a while to get working. I know that Jürgen said that he managed to just do SSH X11 forwarding and get the ANSYS UI to work. So yeah, I mean, let's just start the breakout rooms and we can take it from there in each of the breakout rooms, and I will jump between. Yes, we are back. So I could see from the HackMD that there were some issues starting VNC, but they managed to get the text based report from the profiler. That's great. So before moving forward, I will just show like the profile I got in the GUI. And then what I want to say was that after looking at the profile, let's take 10-minute break. And then we will have a quick peek at my take on optimizing this app. And then we'll conclude with some general consideration, buffer and accessors and unified shared memory. And that would be all for today. So there will be no more breakout rooms after this. So let's look at the profile. So what I did was build, so ask for an interactive job on one of the nodes, build, run the ENCCS profile command with the command line interface, and I got this report1.qd rep. So now I can just call ANSYS UI from the command line interface, and it's not opening, so that's new. Should be there. That's disappointing. Okay, let's do this. Let's open a new terminal. Maybe that's the problem. Module list, module purge. Yeah, didn't see me, but okay, ANSYS UI. And we are back. So I still don't know why we cannot start the profiler. So sorry for that. That was unexpected, and we had, I mean, I had tested earlier that it would work when I got the screenshot there, but we got a tour of the profiling information anyway. And so again, now we have identified where the bottleneck is, and we have to come up with a strategy to overcome that bottleneck. And since the problem is because we're creating the buffers inside a new scope, then there's new copies being triggered every time we get into the scope and out of the scope, and that happens every time step. So what we should do, since anyway these buffers can be reused, so we can allocate that memory to hold the temperature field at the given time point and at the next time point. So we need two of those. We know how large they are. The size doesn't change with time stepping iteration. So we can just allocate them on the device so they're device resident, and then reuse them instead of copying them back in and out to the host, because the host doesn't do anything with this data structure except printing them maybe at the end or initializing them. So the first thing to do, obviously, is to reorganize the code so that the buffers are created outside of the time stepping loop, and that we update the final buffer at the end of the time stepping when we have the final result. So as I outline here, what we would need to do is, okay, create the buffers to the current and previous hit fields, data outside the time stepping loop, modify evolve so that now it accepts buffers instead of field objects. Of course, we could modify the field objects to hold the buffer itself, but that would require some more modifications in the code that are not necessary to make the point of this type along that I'm going to show now. And then also the swap field function needs to be modified, which is the function that takes the previous and current data structures and swaps them so that we're ready to take the next time step. Because instead of working on a field data structure, it needs to work on a buffer. So this is kind of the minimal amount of work that we should do to try to optimize. And then, of course, the code will not be very pretty because we have this field data structure, which we're not really using. We're just taking a buffer to the data underlying it. So maybe we can reorganize so that the field holds a buffer and so on. But this is kind of second order worry that we should have. First, let's make the code correct, then make it run fast, that maybe clean up the interfaces so that the code look is correct, elegant, and fast. So I have written a port now that is optimized according to these 3 points that I've just made. Instead of letting you go through the process of optimizing, I'll just walk you through what I've done. And if there are questions, please let them come through the HackMD, and we can maybe have a discussion on what I'm doing. Here, I'll just take a little bit of water before. So let's start from the main function, so from main.cpp. So the initialization of the data structures, I keep it through this field data structure that we're using. So the initialization still happens on the host. So as a further point, we could still go through the pain of just saying, okay, we know that these data structures will be almost always used on the device, and they're only used on the host when we need to kind of write the PNG image to disk, or at the end when we need to calculate the average temperature over the plate. So we could decide to just initialize everything on the device and then only trigger copies back to the host when we know we actually need it. So even the initialization could be done on the device, probably through that parallel loop. But at the moment, I'm leaving that as it is. Okay, so the initialization happens on the host. That is probably the next step in optimization. Initialization shouldn't be a bottleneck, but you never know, unless you measure with the profiler. So then at the beginning, there's a write field. Okay, this is, again, something, the writing, the I/O needs to happen on the host. And here I've changed the code such that well, I take out the x and the y from the current field data structure, calculate the denominators for the finite difference, delta x squared and delta y squared, and calculate the time step based on that, and the diffusivity. So then I take the size of the grids, and here the static cast, I need to put it in to avoid the compiler error further on. So I don't think it should be required, but put it there. Okay, sorry. Here, better to be explicit and use a GPU selector instead of just relying on hipSYCL and the configuration when we try to build to make sure that we end up on a GPU. And then here I do the following. So I open a new scope where I declare buffers to the current and previous data structure. Okay. So what this does, it takes the data hold by the current field and that by the previous field and maps basically maps them to a buffer. The sizes of this buffer are the same as before, as I was explaining, an x plus 2 times ny plus 2, because we need to take into account the region around that we put in, not to time evolve it, but just to make sure that the stencil does not fall off the grid on the sides. And then we go into the time stepping loop. Here I've left commented out the previous version of the code where I would pass the current and previous field data structures. Here I've modified evolve to get the two buffers, so the Q, the two buffers, and then I explicitly pass diffusivity, time step, and dx and dy squared. Why do I do this? Because now we don't have a data structure that holds this information for us. We're just passing the buffer in, so we need to make the evolve kernel aware of those. So in the next iteration of the rewrite of this code, we would probably, as I said, wrap the buffers inside its own data structure, so things have a cleaner interface, but at the moment, this is enough for what we want to do, so making the code faster. So I've commented out the writing of the field every so often during the iterations, because that would require me to change the write field function to accept the buffer, trigger a copy. So this is something that I don't want to do at the moment, so I just commented it out. So this std swap here was commented out, so I delete it. And then the next thing that I changed is the swap fields function. So yes. So we need to look at what evolve does now and what swap fields does. And finally, after the time stepping loop, I put a wait clause. And that's, we didn't do that before. And that was because at the end, within the evolve function, we had the closing of the scope that triggered the copy back to the host that made sure that the command had completed before the copy was actually carried out. Now we don't have that anymore between time iterations, so we need to make sure that before we move out of this, that we actually wait for all the iterations to be done. And we close the scope, so that would trigger the update of the data that the buffers were pointing to. So both previous and current then hold the value at the last iteration. And that's it, because now both the previous and current data structure add the data that we want, and the rest of the code looks exactly the same. So let's now see evolve. Okay, let's start from swap fields. So the previous way it was implemented was we would pass temperature1 and temperature2 by pointer. And then get the data member of this structure and just use std swap. And this works because this data member is an std vector for which std swap is well defined. So in our case, we pass two buffers by reference. It amounts to the same as passing by pointer, but it's a bit clearer at call point what we're going to do. And again, we can directly call swap on these two buffers, because the buffers do implement all the special functions that are required to implement the swap correctly. So copy constructors and move constructors are implemented correctly. So std swap knows how to handle swapping the two buffers. So this is it for swap fields. So this was quite easy. It was basically copy pasting of the function that we had before and kind of changing the types of the variables coming in. Now, if we look at core.cpp, that had this one gets a bit more changes. So this was the previous version. I've left it in the code because now we can take advantage of function overloading in C++ and just define a function with the same name, but it takes different number of arguments, so there is no ambiguity for the compiler to resolve this. So as I said, we're now passing not only diffusivity and time step as arguments in, as we were doing in the previous version, we're also passing the denominators for the finite difference formula, so the x squared and the y squared. And then we have the q, and we pass the current and previous temperature field buffers by reference, again, because we're going to modify their content, so we're not passing by value. So first thing I do, so I could pass the size of the grids and x and y explicitly in, but I decided to not do that and instead get them from the range of the current buffer and removing 2. I removed 2 because remember that the buffers are defined to be nx plus 2 times ny plus 2 to take into account the region outside that lets us apply the stencil without running into trouble. So I need to apply this minus 2 to get the actual value of an x and y. And these ones are needed because I need them to define the range of execution of the parallel 4. So now the queue submission here and the way we use accessors and the way we launch the parallel 4 has not changed from before. So I've just copy pasted it inside here. The thing that changed is that when we get to this point, the memory is already resident on the device. So there are no copies to be made, but otherwise the application of the stencil hasn't changed at all. So now with this code here, what I will do, which I should have done before, is to request an interactive job and compile it and run it. And then probably I will make use of what one of you found out and just do the stats with the profiler so that we can look. Sorry for the wait. So if any of you is still running an interactive job and hasn't released it, it would be a good idea to do it now. Okay, there is a question. Yes. The wait is needed, but immediately after you close the scope. Yes, indeed, the wait might not be needed. I think that I went through another iteration of that code where I wouldn't be opening and closing the scopes, but rather use, trigger copy by hand on the back to the host. That version was not, I was not very happy with that. So I just went back to the one where I open and close the scopes, but I think the q.wait stayed behind. So one thing that, I could try if I manage to compile is to remove that and see if the code is still correct and gives the correct answer. But yeah, you're completely, you're right. So if with the opening and closing of the scopes, then the wait should be redundant. Of course, what happens, I believe, is that if the event is already done, that the wait will either be a no-op or it won't matter for performance. It might just be a polling request, so it's not that heavy on performance. But yeah, it shouldn't be necessary there. So I was being overly conservative, I guess. So this is not starting at all. Sorry about that. So I suggest that I just go through the last part for today, which was kind of mini guide that should probably help you decide whether you should move to a buffer-accessor model or using unified shared memory. So trying to decide what's the best strategy and what kind of trade-offs you have between the two. So the of course I don't have a rule that is set in stone, and that I can tell you in this case it's always better to use one or the other. You need to carefully consider what kind of code you have at hand that you want to port to SYCL. So you need to first ask yourself if it's okay for the runtime to be in control of decisions when it comes to allocations and data movement and memory management in general, or whether you want to be fully in control. And that's why I prepared this chart. So if you prefer to leave decisions to the runtime, so if you want to take advantage of this implicit way of doing stuff, then the next question to ask is what kind of abstraction level that you want to use. So if you're familiar and comfortable with using C++ constructs, then probably buffers and accessors are something for you. Of course, if you have a large code base that you already have working, and you also need to consider what kind of memory management strategy is already in place, because buffer and accessors might require a larger effort, larger startup effort. So to get started, you need to touch code in more places, probably, just to make sure that you fit into this new framework of doing things with buffers and accessors. But if you're comfortable with that and you're comfortable with modern C++, then that's probably something you should consider. If instead you're worried that that would require too much effort to just get started and try out SYCL, then USM shared allocations, in which the migration between host and device is left again up to the runtime. That is probably the way you would like to go. It's a pointer-based framework that is very familiar from the way you allocate memory in C and C++, so it should not be that much different to get used to it and to start working with it productively. So if instead you want to keep explicit control of what memory allocate and how memory is moved, then you would need to go towards the direction of USM device allocations. So these will look more like CUDA or HIP, so more lower level, but definitely full control over what gets allocated when and how it gets moved around. Again, you don't need to worry too much about additional levels of abstractions or using different abstractions in code that might already be existing. So this chart is, very simple. It doesn't really take into account the effort from the programmer side if there is already a large infrastructure around memory allocation in your code. So that's a consideration for which you as a developer are better equipped than me to give an assessment. I can only give kind of a general idea of what's going on. And one thing that I haven't mentioned is if I use one method or the other, how do I decide, like if at any later point I decide that this is not working exactly as I expected, maybe I should go back and reevaluate the strategy and choose the other. Is there an easy pathway between the two? So unfortunately, that is not something that is already available today. So there is no established way in the standard. So that is standardized and mandated by the standardizing committee to make buffers and accessors and USM interoperable. So this is something that is lacking at the moment, and there is a good reason why it's lacking. It's because USM was added to the standard in with the current version of the standard, so SYCL 2020. And before adding on top this interoperability layer, of course, the committee wanted to get more experience with how USM would work in the wild. So it's not unexpected that it's not part of the standard, but it's definitely something that is lacking, and hopefully it will be added to the standard later. So if you're using hipSYCL, however, as part of the extensions that are in hipSYCL together with the newer version of hierarchical parallel 4, there's the possibility to use this buffer USM interoperability extension. I have not played with it myself, so if you're interested in that, you should read this blog post by the main creator and maintainer of the hipSYCL compiler, and hopefully this gets merged into the standard, and then all this chart here might become obsolete in the future. So let's see. I still don't have a job running, so I cannot show you that this actually performs better. Sorry for that. We cannot look at the profile of this new one to see that the number of allocations has decreased considerably. So I don't have anything else to add to this. So the floor is open for questions through the attendee. And I'm not 100% sure if there's how long the accounts that you have are going to be active. But I hope that at least until the end of today and maybe also tomorrow morning, so that you can try out compiling this optimized code. It's in the day 302 SYCL equation OPT folder. So you can try it out yourself, see that it actually shows a speed up with respect to the serial version and the SYCL non-optimized version. And maybe you can also have a look at the profile to see that indeed we cut down significantly on the number of allocations. So I'm sorry that I cannot show this to you live at the moment, but the job is not going through, so there's not much I can do. And with this, yeah, so yes, I mean, that's it for the workshop. I would like to thank the people that helped set this up. So my colleagues Tur Wikfeld and Apostolos here at production, and of course Andrei, Stigrune, and Jürgen for helping out in the breakout rooms and with the HackMD. That's very, very helpful and very much appreciated that you took the time to attend the workshop again and help out. And all of you for powering through these 3 days. I know that they've been intense, and also the exercises, there's not always been enough time, as many of you might have wished. But yeah, so we're done with this workshop. If you're interested in any other training events that we organize, please visit our website or follow us on Twitter, LinkedIn. We always post stuff there that we're doing.